Okay, so hello guys. So I guess we'll get started in 3-4 minutes so that a few other people can also join. So since there are only currently two of you, so maybe we'll get started in like let's say 5 minutes so that some more people can join the meet. Okay, so since a few more people have joined now, so hello guys, Ram Gopal and Satvik. So I guess we can get started. So just 1 second, guys. So yeah, so hello everyone. I'm just to introduce myself. I'm Lakshay Saggi, the TA for competitive programming course for the Tuesday sessions. So this will be our third session, and in today's session, like every session, we'll be discussing problems related to this week's lecture videos. And in this week, mostly problems were related to greedy algorithms, right? So the problems which we'll be discussing, which will help you solve your weekly assignments, will be based on greedy algorithms only. So I guess we can get started with the problems. I have some 9 problems with me. So yeah, let's just get started with them one by one. So I'll just share my screen and then uh, we can start discussing these problems. So just let me share my screen, guys. Okay, so I hope my screen is visible to everyone. If there are any visibility issues at any point, or there are issues in my with my voice, just feel free to tell me via chat. So yeah, just feel free to stop me at any point if there is some issue with the screen or with the font size or anything in general. So yeah. So other than that, I guess we can get started. So like all previous sessions, I'll be assuming that you guys have went through the lectures. So in this week's lecture, we in this week's NPTEL lectures, there was a problem which was pancake flipping problem, which was discussed. Similarly, there was island war and different problems discussed. So we'll be discussing questions related to these problems only. So first problem is related to the pancake flipping problem. So the problem, I believe you guys must remember the problem that we were given an array of pancakes, a long number of pancakes, and we had an oversized flipper of a certain size, and we could only use that flipper to flip the pancakes. And then was it possible to flip all pancakes such that all pancakes end up on their happy side? So yeah, something like this was the question. So the first problem is just direct uh, question related to that problem and algorithm only. So consider the pancake flipping problem. Let the size of the oversized flipper be 4, and we have happy side and blank side of a pancake. So we'll be denoting the happy side by 1 and the blank side by 0. So the problem now asks which of the following initial set of cookies are impossible to be flipped into all happy sides up. So we are given these all of these options, and now individually we have to check which of these configurations, in which of these configurations we'll be able to flip all the cookies into a happy side. So I guess we can get started with discussing. So we'll have to move with option by option here, since we have to look at all the options and just tell which of the options, in which of the options is it possible to flip all cookies into their happy side. So yeah. So in the answer, just get started with options. So let's just see the option A first. So in option A, we have this sort of array. So initially, the configuration of cookies is something like this. And if you remember, what was the algorithm which was discussed in the pancake flipping problem? That how can we ensure that we'll be able to flip all the pancakes to happy side or not? So the algorithm for this was like something like a greedy algorithm. So the algorithm was, so I'll just write down the algorithm uh, informally. I'll just describe the algorithm informally so that you guys just remember it again. So yeah. So the algorithm was something like this, that s- start from the leftmost pancake, which is on blank side. Flip, then we flip all the pancakes. Uh, then we flip all the pancakes starting from this pancake, starting from the. So what we actually do is maybe I'll just tell you a bit better. So we start from the leftmost pancake, which is on the blank side. So we start from the first 0 from the left, and then we see our flipper size, and we flip as much pancakes as we have to. So like here, the first 0 from the left is this 0. So we'll be flipping 4 pancakes now. So we'll be flipping the 4 pancakes next to it. So something like this. These 4 pancakes will be flipped, and then again we'll be continuing this sort of setting. So flip all the pancakes starting from this pancake using the flipper, and continue this procedure. And if we continue this procedure, and in the end, if we are able to obtain, in the end, if we get all pancakes on their happy side, then we are done. So I'm just informally describing the algorithm because I believe you guys must have gone through the lectures, and this is just sort of a let's say revision or something. So yeah. So the algorithm will go something like this in this case, that we have these pancakes, and now we'll see the first pancake from the left, which is 0. So the first 0 is this. So we'll use the flipper size given to us is 4. So we'll use the flipper and flip 4 pancakes from here onwards. So these 4 pancakes will be flipped. So after flipping these 4 pancakes, maybe I'll just underline the first 0 also. Okay. So yeah. And now after flipping these 4 pancakes, what happens is the configuration becomes something like this. This 0 becomes a 1. This one becomes a 1. This 0 becomes a 1, and this one becomes a 0 because we had flipped these 4 pancakes. So yeah, these 4 have been flipped now. Now again, we look at the first 0 here, and this first 0 actually occurs uh, here. So this is the only 0 which we have now. But now our flipper size was 4. So we can't start from this pancake and get we can't start from this pancake and get 4 pancakes inside our flipper. So actually what this means is that we can't continue our procedure now. So this means that uh, this set of cookies is impossible uh, to be flipped onto their happy side. So I'm just referring to cookies as pancakes also. So cookies and pancakes are same here. So after this, we see that this is the 0, but we can't flip now 4 cookies now, since we don't have 4 cookies to the right of it. So since we don't have 4 cookies, since we don't have 4 cookies to the right of the underlying pancake, uh, we won't be able to get all cookies on their happy side. So something like this. Okay, so I hope the procedure is clear to everyone. So we'll go over the other options also. So option B again is something like this 1 0 1 0, this option. So again, we know that the flipper side is 4. We'll just remember it. And we see the first pancake from the left, which is 0. So I underline this one, and we'll be flipping now these 4 pancakes. Right. So let's just see what happens. So after flipping these 4 pancakes, we have to flip these 4 pancakes. So this becomes a 1. This becomes a 0. This becomes a 1. And this becomes a 0. So this is the configuration now. And now what we have is something like this, that this is the first 0 which we have from the left. So now we'll again underline this pancake. We'll again be starting from this pancake. I just underline, and we'll be flipping these 4 pancakes. So now what happens is what happens is something like this, that maybe I'll just put this in next line. So yeah. So this 0 becomes a 1, this one becomes a 0, this 0 becomes a 1, and this 0 also becomes a 1. And this one is not underlined anymore. Now we have this 0, and this is the 0 which we'll be starting from now. And using this 0, we'll be flipping these 4 pancakes. So if we flip these 4 pancakes, what happens is, so I'm solving this a bit slowly so that uh, everyone can understand it clearly, but we'll be moving a bit faster with the other options. So yeah, I'm just moving a bit slowly so that everyone is able to understand. So yeah. So this is the configuration which we obtain now, and now this is the first 0 which we obtain. So I just underline this one, and now we'll be flipping 4 pancakes from here. So these 4 are the pancakes which we'll be flipping. So these are the 4 pancakes which we'll be flipping. And what happens after we flip all of these is that these 4 pancakes are flipped, so we'll get all ones now. And now we won't underline it anymore. And now we see that all pancakes have actually been flipped to their happy side. So this means that we would be able to flip. So we are able to get all cookies on their happy side. So in option B, we are able to get. Option A, we won't be able to get. Similarly, now let's move on to option C now. So would anyone like to? So guys, you can also try this problem in parallel if you have understood the procedure now. So that you guys can tell me like what the answer should be for these options also. I'll just continue meanwhile to write down the answer myself. So this is the initial configuration. This will be the 0. So I'll just underline this and will be starting with these 4. So it will come something like this. So these 4 zeros will become 4 ones. And now this is the 0 which we'll be starting with. And then again, we'll be able to uh, flip these 4 and obtain 4 ones. So this will become something like 1, 1, 1, 1. Yeah. So we are able to get all cookies on their apps. Now let's go to option D. Option D is something like this. And here, this is the first 0. Now what happens is these 4 will be flipped. So 0 becomes a 1, 1 becomes a 0, this 0 becomes a 1, this 1 becomes a 0. So this is the first 0. We underline this and we flip the next 4. So this becomes something like, maybe I should do it like this. Yeah. So this 0, 1, 0, 0 becomes something like a 1, 0, 1, 1, right? And now this will not be underlined. This will be underlined. So I just underline this. And this array now becomes something like 1 here, and we'll get 3 zeros here. So this will become 0, this will become a 0, this will become a 0, and this one won't be underlined. This 0 will be underlined, and we'll be obtaining 4 ones here now. So note that you can clearly see here that these 4 will become ones, and these last 4 will also be becoming 1. Yeah, something like this. These will also become 1. Why don't align this, and so yeah. So we are uh, able to get all keys on there. So now let's go to option E, which is the last option. So option E is something like this: 0, 1, 0, 1, 0, 0. And here when we use this 0, so this is quite similar to the previous option only. So I'll just be copying the first set of values. So you can see that these values are actually same in both options. Something like this. So this 0, 1, 0, 1 actually becomes, okay, maybe I'll just copy this. Right, and this 0, 1, 0, 1 becomes like a 1, 0, 1, 0. And now this 0, 1, 0, 0 becomes something like a this 0, 1, 0, 0 becomes something like a 1, 0, 1, 1. Right, and then we obtain another 0, and now we have this 0, 1, 1, which becomes. So I believe this is getting a bit boring, but just bear with me, guys, because we are almost done with this question. So yeah. So now this becomes something like a 1, 0, 0, and we have something like a 0, 0, 1. Here we have 4 zeros. Here we have 0, 0, 0, 1, and then 0, 1, 0, 0, something like this. Right. So now if we flip this, what happens is uh, this becomes 1, this becomes 1, this becomes 1, this becomes a 0, and this is not undefined anymore, and this is the first 0 which we obtain. So now what happens is these four values are flipped. So maybe I'll just copy all of this and flip all these four values. So 0, 1, 1, 0, 1. So yeah, something like this. Now this is the first 0. And if this is the first 0, what happens is we'll be flipping this. So this becomes a 1, this becomes a 0, this becomes a 1, this becomes a 1. And again, we see we obtain a 0, but we don't have a size. We don't have four cookies with us. So since we don't have four cookies with a right of underline pancake, we won't be able to get on their happy side. Okay, so I guess this concludes all the options. So in option A, we were able to get all cookies on the happy side. Were not able, we were able to get all cookies on the happy side in option B, C, and D. So the question asks which of the following cookies are impossible to be flipped. So only option A and option E are impossible to be flipped. So the correct answer is hence option A, comma E are correct. So I hope this is clear to everyone. If there are any doubts, any comments, so you can inform me via chat and maybe I can go through it again. I can go over it again. Otherwise, we can continue to the second question then. So second question is now the island war problem, which was also discussed in the lectures. So the second problem asks us that consider the islands war problem discussed in the lecture videos, and we are given the following input. The input given to us is that there are 8 islands and we have 10 requests. So these are the 10 requests which we have. So if you remember what was happening in island war problem, we were given these islands and we had these requests, and these requests asked us to separate these islands in via minimum number of breaking bridges or something like that. So these islands lie on a straight line connected by bridges, and we need to break the bridges, minimum number of bridges, so that all of these pairs of islands get disconnected from each other. So like one should not have a connection with three, two should not have a connection with three, one with four, and so on. So in this problem, the algorithm was discussed in the lecture. So the algorithm was something like this, that sort the pairs in increasing order, or maybe not just sort, well, let's just say uh, break the bridge, break the rightmost bridge to disconnect the earliest connected. Okay, now this becomes a bit confusing. Maybe I'll just say it like this only. Sort the pairs in increasing order of right points. So all these pairs have right hand side points, which are like greater than the left side points. So we sort the pairs in increasing order of their right point. So like this 2 comma 6 will come before 5 comma 8, as 6 is less than 8. And now what we do is break the bridge, break the rightmost bridge, which connects the earliest pair. And earliest connected pair. Repeat till no connected pair remains. So what we do in this algorithm is we sort the pairs in increasing order of their right points. And after sorting these, what we do is we break the rightmost bridge, which connects the earliest connected pair. So what this means is that suppose initially we had like uh, all the bridges were connected, so we had like something like connections from 1 to 8. So all these pairs were connected initially. So now we see the earliest connected pair out of these. So we see the right hand point, which of the following has the smallest right hand point, and this is uh, the pair which has the smallest right hand point, this 1 comma 3 or this 2 comma 3. So actually what we do is we take this 1 comma 3 pair and we break the bridge which is like which connects the part 2 comma 3, because that will be the uh, rightmost bridge which will break this 1 comma 3 pair. So I hope you get what I mean. Maybe I'll just type this out also. And we repeat this till no connected pair remains. So what actually happens is this whole question in the next page. Yeah. So yeah. So first, the sorted order for these pairs will be, let's just write down the sorted order. So what's the sorted order for these pairs? The increasing order will be something like this, that this 3 is the earliest right hand side point. So these would be earliest. So I guess this is correct. Then after 3, there will be the pairs which have the endpoint as 4. So 1 comma 4, and then we can have something like a 5 comma 4. So we can break ties arbitrarily. So this 1 and this 5 are this 1 and this 2. We can break ties arbitrarily for now. If there's some problem, we'll just see later on. And then we also have a 4 here. So this will also come earlier. So this will be a 6 comma 4 here. And yeah. So after this 4, we'll need something like a 5. So this 2 comma 5 comes after this. And then comes this 6 comma 5. And then we have something like a 6 at the right side. So this 2 comma 6 comes here. And then we have something like a 6 comma 7 here. And then we have something like a 5 comma 8. So I hope everyone is clear with how I have sorted. So I have sorted according to the right hand side points. You can see that these are in increasing order: 3, 3, 4, 4, 4, 5, 5, 6, 7, 8. So something like this. And now what we do is we just break the rightmost bridge which connects the earliest connected pair. So all of these initially are connected because we have connections from 1 to 2, 2 to 3, and so on. And now we need to disconnect all of these pairs. So we see the earliest pair which needs to be disconnected. So this is 1 comma 3 is the earliest pair. So first pair is, so maybe we'll go step by step. Uh, Step 1 will be something like this. Step 1 will be earliest connected pair will be 1 comma 3. Earliest connected pair is 1 comma 3. Right. So what we do is break the bridge 2 comma 3. Right. So because the rightmost bridge which connects 1 comma 3. So let's say we have a path from 1 to 3. And now we want to break the rightmost bridge which connects 1 to 3. So there will be a path from 1 to 2 and 2 to 3. So you will break the bridge of 2 to 3 here. So we'll break the bridge 2 to 3 here. And what happens after this is this 1 comma 3 gets disconnected. So we are happy with this. And this 2 comma 3 also gets disconnected because we have broken this bridge 2 comma 3. So actually we have disconnected 2 bridges now. And now we also see next pair, which is 1 comma 4. And you can actually see that 1 comma 4 is also disconnected now because this 2 comma 3 lies between 1 and 4. So something like this. Okay, so also I think I missed something. So actually the right side of these values is not uh, always greater than the left side value. So we have 1 comma 3, 2 comma 3, 1 comma 4, 5 comma 8, 2 comma 6. But this 5 comma 4 should instead be actually written as something like a 4 comma 5, because we need that the right hand side point is greater than the left hand side point. So these 5 comma 4 here we are given in form of this, but what we'll do is we'll first pre-process the input so that 5 comma, so that we write the 5 comma 4 instead as a 4 comma 5, because we need the right side points, right? So 5 is to the right of 4. So actually this will not be a 5 comma 4, but instead a 4 comma 5. Sorry for missing this. And since it's a 4 comma 5, it will occur like along with something like this part. It's 4 comma 5, 6 comma 5, and stuff like this. Similarly, this is a 6 comma 4, so it should be actually written as a 4 comma 6. And if you write this as a 4 comma 6, what happens is you will need to write it after these fives. So something like here. So I hope this is clear to everyone. So the first step was to sanitize our input so that the right hand side points are greater than the left hand side points, because we are looking at the right sides. Okay, so and then we sorted according to the right hand side point. So 3, 4, 3, 3, 4, 5, 5, 5, 6, 6, 7, 8. So yeah. So now we have broken the bridge. Now 1 comma 3, we have broken the bridge 2 comma 3. So we have broken this pair, we have broken this pair, we have broken this pair, because 1 comma 4 also has a path. Similarly, we have also broken this 2 comma 5 because 2 comma 3 lies between 2 comma 5. What we have not broken, the earliest connected pair now remains. What remains is this 4 comma 5. So now we go to step 2. We go to step 2 and we have some earliest connected pair is now we have broken this. This is the earliest connected pair which we have not broken yet, 4 comma 5. So this is the 4 comma 5 pair. So now we actually break this bridge 4 comma 5. So yeah, because 4 comma 5 only has one bridge between it. So the rightmost bridge is that bridge itself, the 4 comma 5 bridge. So you break the bridge 4 comma 5. And now what happens is this pair gets disconnected. Okay, so I again miss something and I'm uh this is 6 comma 5, so it should also be written as a 5 comma 6. Yeah, sorry. Yeah. So something like this, that 5 6 4 6 2 6 6 7 and 5 8. So yeah. So after breaking this 4 comma 5 bridge, this 5 comma 6 bridge still remains connected. This 5 comma 6 pair still remains connected. So we'll need to disconnect this also. And for disconnecting this, what we do is we break the bridge 5 comma 6. So something like the earliest connected pair is something like a 5 comma 6. So we actually break this remaining bridge. So it will look like a 5 comma 6. So now that what we are doing is we have discussed this algorithm in the lectures, and now we are just simulating this algorithm here to get a better feel of what this algorithm is doing and understand it a bit. So yeah. So now we have just broken this bridge 5 comma 6. So after breaking this 5 comma 6, what happens is this 4 comma 6 pair also gets disconnected. Similarly, this 2 comma 6 pair also gets disconnected. And similarly, this 6 comma 7 pair still remains actually. So we'll need to disconnect this also. So what we need to do is we'll need to disconnect this pair also. So we'll need to break this 6 comma 7 pair also. So after this step 3, we'll still need to break 6 comma 7. So what we do is in step 4. So in step 4, the earliest connected pair is something like the 6 comma 7. So we take this and we break the bridge 6 comma 7. And now you can actually observe that now what I'm claiming is now we are actually done. So this will be sufficient to break everything, because the 6 comma 7 gets disconnected, and this 5 comma 8 also is disconnected. So yeah. So we needed to break actually. So all these pairs are now disconnected, and we needed to break actually 4 bridges. So 2 comma 3, 4 comma 5, 5 comma 6, and 6 comma 7. So note that this is not the only possible solution. There may be some other set of 4 bridges also, which could have given us the correct answer. But we needed to just obtain the number of bridges that must be removed. So the optimal number of bridges that must be removed is 4. So yeah. So hence, the minimum number of bridges that must be removed is 4. So I'll just underline this. So I hope everyone is able to understand. If anyone has any doubts here, feel free to ask in chat, and I'll be happy to repeat it. Okay. So otherwise, let's go to the third problem. So third problem is a new problem, so maybe you guys will find it interesting. It's not a problem from the lectures. It's based on a greedy approach only, but it's a new problem. So you need to pay a bit more attention to this one. So guys, the problem says that assume you are given two positive integers n comma x, where n is greater than x. So we are given two positive integers n and x, where n is greater than x. And in each step, what we can do is we can either decrement the value of n by 1 or half the value of n if n is even. So at every step we are given a choice. So we have a number n, we can either reduce its value by 1, or if that number is even, we can also half its value. Both steps are available to us, and it's our choice what step we want to take. And our goal is to produce the target value x in the minimum number of steps. So what we need to do is we were given these two integers, right? N and x. So our goal is to actually produce the target value x. So we are reducing n by 1 in every step, or we are halving n if n is even. So it's our choice if n is even, whether we want to reduce its value 1 by 1 or whether we want to half it. And now we want to go to this value x in the minimum number of steps. So yeah, so I hope the problem is clear to everyone. So we just need to find out what's the minimum number of steps in which we can go from n to x. So for example, I have also given an example here that let's say the n was given to us as 10 and x was given to us as 1. So one valid way to go from 10 to 1 is we have an initial 10 and then we do a -1, and then from this -1 we go to a 9, and we do a -1 again, we go to a 8, and now we just divide by 2. So we go to a 4, we just divide by 2 again, we go to a 2, and we divide by 2 again, and we go to a 1. So the number of steps required was 1, 2, 3, 4, 5. So we needed 5 steps here to actually go from 10 to 1. So now the problem again just asks what is the minimum number of steps required if n is 950, x is 17. So like this this is not that much important, the input variable, but what will be a algorithm for this? So uh, guys in the chat, would anyone like to suggest a possible algorithm for this problem? Like if we want to go from n to x in minimum number of steps, what would be the best possible algorithm to obtain the minimum number of steps? So please try to attempt it, because I believe a similar question is also present in this year's assignment, and this is an interesting problem, and it is not from the lectures either. So just think that what could be a possible algorithm to obtain minimum number of steps. Like let's just ignore this input, but just let's say we are given a generic n and x, and we want to go from n to x. So what would be a good algorithm according to you guys? So so let's just take 2 minutes to think about this. And if anyone has any ideas, just like you can throw any idea which you have in your mind. Like one hint is this is a greedy lecture, right? So you can do something like a greedy. Okay. So Rahul is suggesting an algorithm that reduce n by 1 till n is a power of 2. And then after n is a power of 2, just reduce it by divide by 2 again and again and again. So uh, Rahul, so note that actually till n is a power of 2, and then you are saying we'll just keep dividing by 2. But note that x need not be actually equal to 1 always. Like in this example, I had given x is 1, but in this problem which we are asking about x is 17 actually. So even if you obtain n is a power of 2, you will be, if you divide by 2 till it becomes 1, so that will not be actually what we want. So yeah. But even if so, one thing, another thing which I would like to point out is Rahul, so even if let's just suppose I had given you x equal to 1 actually, then also the algorithm which you are suggesting is actually won't be optimal. So as you can see here, like this is so when x was 1, I had employed something like this in this example, right? We went from 10 to 9 to 8 till it was a power of 2, and then I did 8, 4, 2, 1. So this took something like a 5 steps. But suppose I did something like this instead. I took a 10, I initially divided it by 2, and this gives us a 5. And then I subtracted 1 because when we obtain an odd number, we can just decrement it by 1 because we can't half an odd number. So I just make it 5 to 4. And now what I do is I divide by 2, I obtain a 2 here, and then I divide by 2 here, and then I obtain a 1. So this sort of algorithm takes actually, this sort of steps take only 4 steps. 1, 2, 3, 4. Even if X was 1, Rahul, your algorithm was sort of, so it was a nice advantage because like it was inspired by this example which I had given, but actually that won't be optimal because as you can see here also that your algorithm takes 5 steps, but I have an example which actually takes 4 steps instead. So even if x was equal to 1, I don't think that's the best algorithm which you could do. So maybe something else would be needed. So I'll give you guys, so maybe you can also take advantage. Like I have given you this example now, so maybe you can think about it using this example also. Uh, okay, so Rahul says that I think we can reduce n by 1 till n is a multiple of x, then divide repeatedly. So Rahul, n is a multiple of x. Why would n? Uh, so you can only divide by 2. You can't divide by, you can just half the value of n. So let's say n was a multiple of, no, no, x is not a prime number, Rahul. X can be any number. Okay. And even if x was a prime number, so what I'm trying to say is, if we reduce n by 1 till n is a multiple of x, so let's just say uh, we obtain, as let's just say we had n equal to 10 and x was equal to 3. So what you're saying is I reduce n by 1. So I obtain like I reduce 10 by 1 and make it 9. But now I can't divide, right? Even if 9 is a multiple of 3. Okay, okay, you did not get the question. So I'm just repeating the question again that we can, what we can do is we can just reduce the value of n by 1 or we can just halve the value of n. And this second step can only be done if n is even. So if n is odd, we just have one step, one thing which we can do, we can decrement it by 1. But when n is even, we have two possible cases. We can either decrement or we can halve. And that's the choice which we want to make. So yeah, something like this. And we want to produce this target value x in the minimum number of steps. Okay, so maybe you guys can think about it for 2-3 minutes more. Meanwhile, I'll just go and fill up my water bottle so that I can get some water. So just think about it, guys, for 3-4 minutes also. And you can also take inspiration from this example, the second example which I have given. The first one was sort of not so, it was suboptimal, but this, what I'm doing here, may be beneficial to you guys thinking about what's happening in this example. Yeah. I'll just come back in 2-3 minutes and yeah, just think about it and then, guys. Okay, so was anyone able to think about it? Okay, let's just maybe make the problem a bit relaxed. Maybe let's just not take these two integers. So let's just assume that x equals to 1. So you are given two positive integers. X n is n comma x, where n is greater than x. So yeah, let's just assume that x is equal to 1 only. Let's just say that you are given a positive integer n. So I'm making this problem a bit easier. N. And in each step, you can either decrement n by 1 or half the value of n. Your goal is to produce the target value 1. So what we actually want to do is we want to produce 1 now in the minimum number of steps. So for n equal to 10, what we want to do is for going from 10 to 1, there are these two possible ways. So now what's the minimum number of steps required when n equal to 950? So let's just relax this problem a little. I don't think taking a general X gives us any more insight. So yeah, let's just take this problem. Okay, so Rahul has come up with a solution. He says that greedy step would be to divide by 2 as much as possible. When the number is odd, make it even. And if the number is even, divide by 2. So this is the first job. This is the first step. Yeah. So yeah, actually, so Rahul, what you are thinking is actually correct. So so basically what Rahul is saying is that whenever the number is even, just divide by 2, and whenever it is odd, we don't have a choice, just decrement it by 1. And actually this will be the optimal algorithm here. So let's just say we are going from n and we want to produce a 1 out of it. So the algorithm will be something like this, that whenever n is even, divide by 2. When n is odd, uh, decrement 1. So something like this, when n is even, divide by 2, and when n is odd, decrement by 1, and repeat till n equals 1. So we have to repeat it till n becomes 1. So yeah, actually this is the correct algorithm, Rahul. And this actually, so yeah, so Rahul gives us a good step to think about, and he says that this is the first job, but we also have to think, why will this be the optimal, right? So we know that sometimes greedy algorithms are actually not optimal. So we have to sort of think that why will this algorithm be optimal here? Sometimes greedy algorithms are not optimal, right? So maybe I'll not show this here, why will this be optimal, but I'll give you just I'll just give you an idea of why is this actually optimal. So just consider that so let's just maybe uh, proof for why is this algorithm optimal, maybe why is the above algorithm optimal. And the hint is something like this. So consider an algorithm, consider another algorithm, or maybe consider another sequence which is better than the sequence produced by our algorithm. So what I mean to say is, let's just say our algorithm produces sequence something like this. It first takes the number n, then it divides by 2 or reduces by and something. So let's just call the next number which comes out to be n1, and then the next number which comes out to be n2, and this goes on till we obtain a 1. And let's just say there are some k numbers in this sequence in our algorithm. Our algorithm's sequence A is something like this. And let's say the optimal algorithm or the algorithm which is better than the sequence produced by our algorithm is something like a, maybe I should put it like this, nk comma 1. So let optimal algorithms sequence, let's just call that sequence O, let that sequence be, so we are starting from this number n only, and I'll just call this something like this number as O1 instead of N1 to denote that the is something like a optimal. O1, O2, and this goes on till something like a OK prime, O of K prime, and then this goes to something like a 1. And and we know that the length of this sequence is actually shorter than this sequence. And why is this so? Because we had assumed that our algorithm is not optimal, right? So the sequence produced by our algorithm is actually larger than the optimal algorithm sequence. So what this means is that the numbers here, the numbers in between here will be less than the numbers in this sequence. So this means that so k prime should be less than actually k. So k prime is less than k. So these numbers are actually less than these numbers. The not their values, but the number of, but the length of this sequence is less than the length of this sequence. So something like this. And now I actually, what I'll give, what I'll tell you guys is maybe just consider the first time uh we divide by 2 in the sequence A. So there are these two steps possible, right? Either we divide by 2 or either we decrement by 1. So what I'm saying is consider the first time in the sequence A divides by 2, and consider the first time the sequence O divides by 2. So these are two different sequences. And so these are actually two different sequences. So the first time this sequence divides by 2 may be different from the first time this sequence divides by 2. And from that, actually, you can derive that our algorithm will be optimal. So I'm just giving you a hint. You can fill in the blanks yourself because I believe you guys must have gone through the lectures and you might know how to do this. So, but I'll give you a basic idea. So just consider the first time that A divides by 2, but O does not. So yeah. So yeah, this is the intuition, and you guys can try to show using this idea that uh, that the that actually O can't be shorter than A. So something like this will happen. So, and the intuitive idea is something like this. So we want to reduce the value of n by as much as possible. So if we are having n, we are actually reducing it by much more than by just decrementing it by 1. So that's why this is the greedy idea here. Okay, so this is sort of, you guys can think of this as your homework. Like, why is the algorithm optimal? So you can just think of this as a homework. I'll just, or not a homework because you guys don't have to submit it anyway, but something like a do it yourself. And the hint to this is something like this. Yeah. So if we are clear with the algorithm that this is the optimal algorithm, then the problem becomes quite clear that we have this 950. So initially n is 950. So maybe we just write. So for n equal 950, the optimal sequence is, so initially we start with 950, and since 950 is even, we divide it by 2. So on dividing by 2, we'll obtain something like a 475. We reduce it to 474. Again, we divide it by 2 because 474 is even. So we obtain something like a 234. and 234 is okay, not 234, but 237. And when we obtain this 237, we'll need to reduce it by 1. So we'll obtain something like a 236 divided by 2, and we'll obtain. So I'm just doing these calculations a bit faster because, yeah, we'll have to cover other problems also. It will be 118, and this will become something like a 59. This reduces to 58. Then this reduces to 29. This is odd, so we'll reduce 1 to 28, and this will become 14. 14 becomes 7, and 7 becomes actually 6. 6 becomes 3. 3 becomes 2, and 2 becomes 1. So the optimal sequence for 950 will look something like this. It takes a lot of steps, but yeah, actually it finishes. So Rahul is typing in the chat that when a number is even, it would take us less steps to reach n by 2 from n. If we divide by 2, then decrementing by 1 will take n by 2 steps. So yeah, Rahul. So this is sort of what you have written is also a part of the intuition, or let's say a sort of idea for why will this algorithm be optimal. But we know that sometimes intuition or the ideas fail, right? Like the sometimes greedy idea we think is correct intuitively fails. So we need to actually make sure that what we are thinking is actually optimal. So that's why I'm saying maybe we can think of it in a more organized manner. So it's like looking at the sequences and then proving that uh, no sequence can exist such that its length is less than our algorithm sequence. So that's the only reason I'm telling you guys in this format. But yeah, the intuition is something like this only, that we need to go to n by 2 as fast as possible. So just coming back to this, so the number of steps taken here will be 1, 2, 3, 4, 5, 6. So it will be 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we are able to reach from 950 to 1 in 15 steps. So minimum number of steps is 15 if n is 950. So yeah. So I hope this is clear to everyone. If there are any doubts, you can ask me in chat. Otherwise, I'll just move on to the next question then. And I'll just underline this. So yeah. Okay, so since no one asking any doubts in chat, I'll just move on to the next question. So maybe I'll yeah. Okay, so it's again a question, a similar question to what we had done. So we are given a set of events E1 to E11 with their start and end time. And a journalist has to attend as many events as possible. And if any event finishes at time T, then the journalist can attend other events starting at time T or afterwards. So so basically we are, let's say, instead of journalists we are present at an event, and there are like 11 events going on in parallel at different start and end times. Since we are only one person, like we can't be present in multiple rooms at once, right? We can only at one time be present in one of these events. And now what we want to do is we want to maximize the number of events which we attend. We want to maximize, let's say, the number of events which we attend, and we are given the start and end time. So an event starts at that. So let's say this event starts at time 3 and ends at time 6. So if I decide to attend event, I'll have to stay for this interval, this 3 to 6 interval at event's venue. And only after that I can move on to some other venue. So something like this is the problem. And now the problem is, what is the maximum number of events that the journalist can attend? So again, we are just given sort of this input, but we'll need to obtain an algorithm to obtain. So first we'll need to discuss some sort of an algorithm, right? Like if we are given just this arbitrary start and end times, then what will be a good algorithm? to actually maximize the number of events which we can attend. So, any ideas, guys? What could be a possible algorithm for this? So, we are talking about this fourth problem here. I'll give you 2-3 minutes to think. So, I'm just claiming that this problem is very similar actually to the bridges problem. So, the where we needed to break the bridges. So, this problem is actually the algorithm. The correct algorithm would be actually quite similar to the bridges algorithm. And I believe this is quite a famous problem. So, okay. So Rahul is saying always choose the shortest duration event after finishing the last attended event. And what would be the first event to attend is something to think about. Okay, so Rahul, what you're saying is that we should always choose the shortest duration event after finishing the last attended event. And so, but what I'm actually saying is this idea, so this is a good attempt and this is one natural approach which comes to mind, right? We want to spend as little time in events as possible to maximize the number of events. But actually this greedy idea actually fails, and you can actually construct examples for this also. So this is actually similar to the bridges problem also. So in bridges problem in the lectures, we discussed like why various approaches might fail, like max the like deleting the bridge which max occurs in maximum number of pairs, something like that. So we tried different algorithms, but they fail. So you similarly you can find examples for which fail for this algorithm also, the algorithm which you are suggesting that always choose the shortest duration event after finishing the last attended event. It's a good attempt, but it's actually not the optimal algorithm. So just putting it out there, maybe you guys can think about it yourself. Also, the optimal choose the event with the attended event with the smallest end time. Or maybe just choose the available event with the smallest end time. So actually, this will be repeat till no event available. So actually, in bridges problem also, what I was saying was we choose the bridge which has the smallest right and to so that choose the available event with the smallest end time and repeat till no event is available. So actually, what we do is so just an oral run for this. So actually, these activities are already sorted in their increasing order of the end times. So what we actually do is we choose the smallest end time event, which is this event E1. We attend it. So from 3 to 6, we attend this E1 event. And after this, we see which event now becomes available. So this E2 is not available as it overlaps with 5 to 7. This E3 is also not available as it overlaps with E1. This E4 is actually available to us because after 3 to 6, we can again go from 7 to 9. So next we attend this 7 to 9 event. And similarly, we move on till we find another available event and we attend it also and something like this. So this is actually the optimal algorithm here. And why is this optimal? Uh, Again, this is something I'll give you guys. Mhm. maybe you guys should think about this yourself. Why is the above algorithm optimal? So again, it's a do it yourself problem. So, and I'll just again give you some sort of a hint. So again, the hint would be something like this that uh, consider the earliest finishing event. Okay, so the earliest finishing event which you take, the earliest event, this even was the earliest finishing event here, right, guys? So suppose there was an optimal solution which did not include this even. So suppose there was an optimal solution which did not include even. So that means in this this 3 to 6 time slot would have been occupied by some other event, right? Because if there was no event going on between 3 to 6, then we would have chosen even. That will be only optimal. But if an optimal solution does not choose even, that means that this 3 to 6 slot is occupied by some other event to the right of this even. But note that let's just suppose that this 3 to 6 slot was instead occupied by E2. So the optimal solution consisted of saying that we schedule E2, we visit E2 event. So we go from to 7 to event E2. So instead of going to E2, it would have been actually better to leave E2 and go to E1 instead. Because I'll be free by 6 if I go to E1, and I'll be free by 7 if I go to E2. So suppose the optimal solution actually went to E2, I can say that it is always better, at least good, as good to visit E1 as visiting E2. So we'll not be worse off if we visit E1 instead of E2. So this is the sort of argument here. That suppose that E1 was not visited, then some other event would have been taking place in E1's time slot. And then since E1 is the earliest ending event, what I can say is maybe it was better to visit E1 instead of the event which overlaps with E1. So I hope the algorithm and the idea behind it is clear, like why are we arriving at ourselves. So just consider the earliest finishing event. Uh, if it is not scheduled in the optimal solution, then some other event overlaps with it. But it would be so consider the earliest finishing event. Let's say that we call this event E1. And if it is not scheduled, then some other event, let's say the event is E2, which overlaps with it. E2 overlaps with it. But it would be, but we know that we had E1 was the earliest finishing event. So what this means is that E2 finishes later than E1, right? Later than E1. So what this means is that we would not be we would not be worse off if we go to E1 instead of E2. So this is the hint, or basically this is more or less the whole reasoning of uh, why is this the algorithm optimal. So uh, suppose there was this event E2 which we went to instead of E1, but we know that E2 finished later than E1 because E1 was the earliest finishing event. So what this means is that instead of going to E2, we could have went to E1 and we won't be worse off. So that's why. So there may be multiple possible optimal solutions, but this algorithm will always give us one possible optimal solution that repeat the available event with the smallest end time. Note that not the smallest duration, but the smallest end time. So we are just looking at this end time here. So I hope this is clear to everyone. If there are some doubts, you can definitely ask me via chat, because this is again a bit of a new question, but this involves similar arguments to the ones which we have done earlier. So if there are no questions, we can just uh, do this question for this input. So the input is something like this. This start and events are given to us. And now we need to answer what is the maximum number of events that we can attend. So we just uh, do this algorithm. We just run this algorithm over this input. So what happens is the earliest finishing event is even here. So we see that these events are already sorted by end time. We also, okay, let's just not write like this. So we just see that these are already sorted via endpoint. So we can just see the earliest ending event will be the E1, and after that E2 finishes, and after that E3, and so on. So we just look at E1 here. So first we go to E1. Then what happens is we are busy from 3 to 6 at E1 event. So we can't go to E2 because E2 is overlapping with E1. Similarly, we can't go to E3 because E3 also overlaps with E1. But we can go to E4 because E4 is from 7 to 9. E1 was from 3 to 6. Then go to E4. So we can go to the event E4. So now we have went to these two events, 3, 6 and 7, 9. So we are now busy from, let's say, like 3 to 6 and 7 to 9. So now what happens is after this E5 shows up, E5 is from 5 to 10. So it again overlaps with E4. So we can't go to E5 either. Then we go to E6, and E6 also overlaps with E4 because 7 to 11 overlaps with 7 to 9. So we can't go to E6. We can't go to E7 either, but we can go to E8 because E8 is from 10 to 13 and E4 was from 7 to 9. So we can go to E8 now. Then to E8. So at 10 to 13, we go to E8. Then E9 is 10 to 14, so we can't go there. We also can't go to E10 because it is from 4 to 15. But we can go to E11, which is from 14 to 16, and E8 was just 10 to 13. And finally to E11. And finally to E11. Okay, so I hope this makes sense to everyone. Like I just ran this algorithm on this input, and yeah, we just obtain that we can go to these 4 events. This will be the optimal solution. That note that there can be more multiple optimal solutions, but the value of the optimal solutions will be the same. So there may be multiple solutions which visit 4 events, but the optimal will be 4. Yeah. So these are 4 events. So the answer will be a maximum number of events is equals to 4 that can be attended is equals to 4. So I'll just underline this also. And this is the answer. So yeah. So I hope this sort of idea is clear to everyone. And if it is not, you can ask me via chat. Otherwise, I'll just move on to the next question now. Okay, so fifth question is, in the previous question, which of the following greedy strategies would always work correctly? So this is, I think, uh, not a question at all. I just removed it right now because this was just asking what will be the algorithm for this question, and we have already given the algorithm here. So yeah, no point in asking that. So now we have another question which says, so these type of questions are actually, yeah, somewhat interesting because these sort of scheduling problems are somewhat interesting and sometimes not trivial. So now next problem is again based on start time and end time of activities, but this has a different flavor to it. So now what we are given is for an activity X. So let's say there's an activity X. We denote by XS the starting time of that activity and XC as the ending time. So this S is a subscript for start This E is a subscript for N. And following are the start time and end time of activities A, B, C, D, E, F, G, and H in chronological order. So we are given these start and end times in chronological order of activities. So what this actually means is that first the A activity starts, after that B starts, after that C starts, after that A ends, after that D starts, after that E starts, and after that C ends, and after that B ends, and F starts, D ends, and so on. So I hope you guys are able to parse the input, like what does this even mean? So again, just reiterating what this means is that first A starts, and after that B starts, after that C starts, and then A ends, then D starts, E starts, and so on. So note that every activity that starts will also be ending. So like there will always be a XE matching with an activity XS. So A start and AE, BS will be matched with a BE, so there will be a BE. So similarly, like all activities, and also note that always an activity will be ended later than that starting of that activity. Something like this. So now what is the minimum number of rooms required to schedule activities? So earlier problem in this fourth problem, what we wanted to do was we wanted to attend maximum number of activities after this. So we are only one person and we had these 11 events. So we had to maximize the number of events which we could go to. But now in this fifth question, the problem is a bit different. Here we can't leave out any activity. Here the problem is asking that we have to schedule every activity. So all activities take place in, let's say, some room. So one activity in one room, only one activity can be performed at a time. So the problem is asking us that we want to schedule all the activities, right? So what will be the minimum number of rooms which will be required to schedule the activities? So what we want to actually see is the minimum number of rooms required. We want to schedule all the activities, but we can take multiple rooms also. So what is the minimum number of rooms required to schedule these activities such that there are no conflicts? And note that at a time, only one activity can be present in a room. Obviously, you can't have two activities in the same. Something like this. So again, this is a bit of a new problem, guys. Not this is not in the lectures, but this is again an important problem. So uh, would you guys? I would say that you guys should think about it. Let's just maybe you guys can think about it for like 3-4 minutes and yeah, suggest something in chat. Like what can be done in this case? Just think about it for 2-3 minutes, guys. Okay. So Rahul is saying that if an activity is starting, allocate a room count plus equals 1. If activity is ending, count a minus equals 1, and we can track max of count to answer the question. So yeah, Rahul, exactly. That's the idea. So you're correct here that this will be the correct idea here that so what we do is we start from the leftmost time. So we start from here. And what we do is whenever an activity starts, so we have to allocate a room to that activity, right? So we just allocate a room to this activity. And now another activity starts. So the earlier activity has not ended, another has started. So we just increase the number of rooms. Another activity starts, so we just increase the number of rooms again. Now one activity ends. So what this means is that we can vacate one room now. So the number of rooms which we are currently using reduces by 1. So initially we need at this time, we'll just need one room to schedule A. Now at this time, we'll be needing 2 rooms to schedule A and B. Now we'll need 3 rooms to schedule A, B, and C. And after this, after this point, we just need only 2 rooms. Like we have allotted 3 rooms, and out of them, one room becomes available because A has ended. So now we just schedule D in the room which A has vacated just now. So the maximum number of rooms still remains 3. So E starts, and now we need another room, so we need the room 4. But C ends, so now again one room becomes available. So the current used rooms are only 3, and B ends, so now 2 rooms become available. So F starts, so something like this. So the idea given by Rahul is actually correct. Maybe I can just even copy paste your idea here. So the algorithm will be this. So start from the left. So start from the leftmost side. What I mean is start from here, that we'll need to look at the leftmost activity first. And if an activity is starting, allocate a room count plus equals 1. If an activity is ending, count minus equals 1. And we can track count once. So with that, we obviously need to allocate a room to it. So we count equals plus equals 1. But whenever an activity ends, we can just we sort of have vacated the room. So the rooms which we are currently occupying reduces by 1. So yeah. So this is and so what this count actually is giving us the number of rooms at any point which we are using. So this count variable actually gives us the number of rooms which we are actually using. And so the number of rooms which we would be required, the number of rooms we actually will require for scheduling all the activities will just be the maximum of count, because it will be the maximum of the number of rooms which we need at any point of time. So yeah. And why is this optimal? The idea is, again, the idea here is that count stores the number of rooms which we are using at any point in time. So max over all times gives us the total number of rooms required. So yeah, something like this. So I hope this is clear to everyone. So yeah, if there are any doubts, you can ask me. But otherwise, this is the idea which we'll be using here again. So here what happens is, okay, so how do we do this? So initially we had the count variable as 0. And now what happens is this activity. So I have just copied this here again. Okay, maybe I don't need to copy. So initially the count variable was 0. And now what happens is this AS comes up. So I'll need to allocate a room to that. So it becomes 1. And as soon as this I schedule this AS, now this BS comes up. So I'll again need to schedule a room for it too. And then the CS comes up. So I'll need to schedule a room for it. So this becomes 3. And now A ends. So one of these rooms becomes empty. So 3 goes to 2. Now D starts. So this 2, we need to allocate a room. So 2 goes to 3. Now E starts, so this 3 goes to 4. And now actually C ends. So C ends, so the 4 becomes 3 now. And now B also ends, so this 3 becomes 2. And now F starts, so this 2 becomes 3. And after this D ends, so this 3 becomes again 2. And after this G starts, so this 2 becomes again 3. And then E ends, so this 3 becomes 2. And then H starts, so this 2 again becomes 3. And this F ends, so this 3 becomes 2 again. Then G ends, so this 2 becomes 1. And H ends, this 1 becomes 0. So note that we will always be, if we are starting at 0, we'll always be ending at 0. And why is this the case? Because every starting activity will be ending. So in the end, we'll be vacating all the rooms required, right? The track of count is, so the track account, or maybe just this count, is something like this, that becomes 0 to 1, 2, 3, 4, 2, 3, 4. So note that over all these values, the max of count is actually 4. So we'll be needing actually 4 rooms minimum. Hence, the minimum number of rooms required is equals to 4. Right. So I hope this is clear to everyone. If there is any doubts, you can ask me via chat. Yeah. Okay, then. So maybe we can move on to the 6th question now. So the question asks us that consider the following 4 items, 1 unit for each with their weights and values. So we have 4 items. So we have one item which has a weight of 7 and a value of 28. We have another item, a weight of 10 and a value of 60. So we have these 4 items with us with weight 7, 10, 2, and 4 and values this much. And 1 unit of each item is valid. So there are not multiple items, but they are just 4 items. And now what we want to do is we want to pick a subset of these items. So we can't pick, let's just say we have a bag and we want to, uh, and every item has a value. So we want to take maximum value with us. So we want to take those items with us, which gives us the maximum value. But our bag also has a capacity. Like we cannot carry more than, let's say, 13 kg. So the maximum capacity it can carry 13 kg. So obviously we cannot carry all the items together because all these items together have a weight of 10, 17, 19, and 23. So we'll need to make some choices here. So what we want to do is we want to maximize the total value which we obtain, which we can carry, and we need to maximize it while ensuring that the maximum capacity is 13, right? So let's say the optimal algorithm gives us, let's say the optimal solution to this problem, let's say how much we can carry is, let's say v opt, and we define v greedy as a, so let's define a greedy algorithm for this. So we are given weights, we are given values, and we want to maximize the total value given a constraint on the weights. So one idea which naturally comes to mind is, oh, maybe what I can do is I can carry those items which have maximum bang per buck, something like this. So basically, which have maximum value per unit weight. Because I have a restriction on weight, I need to maximize the values. So maybe the best idea maybe to carry the items which have maximum value by weight ratio. So yeah. So this is the greedy algorithm, that the total value of items picked by one greedy approach is that it sorts the item by value to weight ratio in descending order and picks them greedily starting from the first item. So I pick the item with the maximum value by weight ratio, which I can carry in my bag. And after this, the next item which I can carry in my bag with the maximum value to weight ratio and so on. And I do this till my weight capacity has not exceeded. So yeah, so something like this. So this is the greedy. So this is the, let's say, the value greedy, so this is the greedy approach. And let's say we call this the V greedy, the value obtained for this problem. If I follow this V greedy, and let's say V opt is actually the total value of items picked by an optimal algorithm. So one preface, like I'll just give you guys, is that this greedy algorithm actually does not work here. It does not give us the optimal value. So this is something called the knapsack problem. You learn about it more in dynamic programming, but this problem is just for an introduction to you guys that greedy does not always work. So the problem is saying that let's suppose we have a greedy algorithm and we want to find out what's the optimal value also. And we want to see what's the difference between the opt and greedy values. So yeah. So a simple problem, it just shows us that sometimes greedy is not the optimal. So okay, so Rahul is saying that uh, so Rahul, actually you're saying that the pick the item with maximum value such that total weight is less than 13, then pick the next item which has maximum and total weight is still less than 13. So actually Rahul, this algorithm is also not correct. So actually, this problem cannot be solved by a basic greedy algorithm. It's called knapsack problem, and it requires something like dynamic programming. So here we'll just have to see by ourselves, like what would be the maximum. We'll just need to see it by ourselves. So we will not discuss an algorithm for finding the optimal solution as of now. So we won't discuss an algorithm for finding an optimal solution for this problem, but we'll just see this input instance and just see by ourselves, like what would be the best way to carry the weights, to carry the items. So let's just look at the V greedy first. Let's look at the consider the items collected by greedy. So what will be the items which will be collected by greedy? So it sorts them in descending ratios of weight by value, right? Value by weight. So what this means is that this will have a weight by the weight by value ratio for item 1 is actually equal to something like a 28 by 7, which is a 4. Similarly, for item 2, it is actually 60 by 10, which is 6. For item 3, so maybe I should put this as a calculation also so that people don't get confused from where did this come. 60 by 10, which is 6. Then item 3 has something like a value of 24 and a weight of 2. So it will be something like a 24 by 2 is 12. And then this fourth has again 28 by 4, which is 7. Item 4 is 28 by 4, which is 7. So yeah. Okay, so we have this bang per buck for all the items, and we now see that the maximum weight by value ratio is for item 3. Okay, so item 3 has a value of 10, 12. So what this means is that we'll first pick item 3. So greedy first picks item 3. So after picking item 3 has a weight of 2 kg. So we are only left with, so we need 13 kg. So we have already filled ourselves with 2 kg. So only 11 kg is left. Only 11 kg more can be collected. So only 11 kg more can be collected. The 11 kg more can be collected. And now what we do is the next best after this, the next best item is after 12, the best bang per item is item 4. As uh, after 12, this is the largest value, the 7. So item 4 will be the next item which we can pick. And it has a value of 28 and a weight of 4. So then it picks this item 4, which weighs. So this item 4 actually weighs 4 kg, right? So now only 7 kg more can be collected. So uh, we we collected this item 4 and it had a weight of 4 kg, and we initially had 2 kg weight also. So now we only have left with 7 kg more weight. And now after this 12 and 7, this side we collected this item 2, which has a weight of 10 kg. But note that the constraint is that we cannot carry now 10 kg because we only have a 7 kg left. So instead, so we'll ignore this item 2. We can't pick up this item 2. And now we go to the last item, which is item 1. And it has a weight of 7 kg. So it actually can be picked. So item 2 not be collected. So it picks item 1. Now it is now full. So finally, the greedy algorithm picks item 3, item 4, and item 1. So the greedy algorithm picks items 1, 3, and 4. So what's the value given to because of these items? So the V greedy will be actually equal to the value which we have, the value from item 1, which is a value of 28, plus item 3, which has a value of 24, and plus item 4. Okay, so item 1 had a value of 28, item 3 had a value of 24, and item 4 had a value of 28. So yeah, so 24, 28 plus 24. And this will actually be equal to 28 plus 26. It is 56. 56 plus 24 is 60 and 80. So V greedy will actually be equal to 80. Okay, guys. And can actually, so now we don't have an algorithm to find the optimal, so we also need to find out the V opt here, right? We have found out this V greedy that is actually equal to 80. We also need to find out what's this V opt. And uh, we don't have an algorithm for this as of now, since we are not discussing dynamic programming. So we'll just need to look at this and find out the best possible weight ourselves. So would anyone like to point out what would be the best possible value which we can obtain if we can carry only 13 kg? So from these 4 items, how can you make the weight 13 kg and get the maximum possible value? So this does not involve any algorithm. You just need to check for all possible combinations and see which of the following will have the maximum value. So I believe this is something which you guys can do yourself also. So I'll encourage you to try this. So the weight should not exceed 13 kg, but you need to maximize the value. So any ideas what items should be carried to? Okay. So yeah, so Rahul actually saying that we can obtain a value of 84 using the weights 10 and 2. So yeah, so Rahul is saying we can collect this weight of 10 kg and we can collect this weight of 2 kg, and this will give us a total value of 84. So yeah, actually Rahul, this is the optimal value. So good job, Rahul. So V opt is actually equal to uh, in the optimal solution, or maybe it can be seen that the optimal solution is to pick items 2 and 3. And what would the V opt here? And V opt here would be nothing but item 2 has a value of 60, 3 has a value of 24. So it will be something like a 60 plus 24, which is 84. So you can see that V opt is actually greater than V greedy. V greedy was just 80, V opt is 84. So what this means is that we needed to find out this V opt minus V greedy. And this will actually be equal to 84 minus 80, which is 4. So yeah, something like this. So this is the correct answer. I just maybe underline this. Yeah. Yeah. So good job, Rahul. So yeah, this is the value of V. And this is the answer. Yeah. The 4 is the answer. Okay, so I have two more problems to discuss. Mm, what should I be discussing now? Maybe only have time for one more problem and not for all the problems. So maybe this coins problem can be skipped because this is something which you guys. Okay. Okay, maybe I'll skip this eighth problem then. Yeah. We'll just do the seventh problem and then we'll wrap up. So yeah. So the seventh problem is because I think this is similar to problems in assignment. So this will help you more than the eighth problem in assignments. So yeah. So this problem states that let coins be a list of k coin denominations. So we are given k coin denominations and every coin is available in as much quantity as we want. And let's say we want to pay a sum of rupees X using as few coins as possible. So let's say so these are the actually five options. So these are the five inputs. So one time, let's just say we are given these coins, a 6 rupee coin, 1 rupee coin, 5 rupee coin, and 7 rupee coin, and we want to give 15 rupees to someone. Similarly, we are given these 10, 1, 2, 5, and we want to give 25 rupees. And similarly for all other options, all these options also. So these are the possible inputs. And now let's say we suggest this greedy strategy. And what's the greedy strategy? Let's just say we sort the coin denominations in the descending order. Okay. So let's just say I sort the coin denomination in their descending order, and then we repeatedly choose the largest coin denomination that is less than or equal to the remaining amount X. And we subtract the chosen coin value from X and continue this process till X becomes 0. So what we do is we just choose the largest coin denomination, keep choosing it till the largest coin denomination, till X becomes smaller than the largest coin denomination. And then we like sort of keep proceeding in this manner. And now this is the greedy strategy one suggests. And note that this was discussed in the lectures also that this greedy strategy is not always correct. But we did not give an exact criteria when it is not always correct. So yeah, there's not an exact characterization of when is it not correct and when is it correct. But so we'll have to check this ourselves manually. So let's just say also the question is asking let's just choose all the counterexamples which prove that the greedy strategy is not optimal. So so we need to find out in all these examples the greedy strategy will select some amounts, right? So we need to make those amounts and see whether that amount can be made in lesser number of coins than what the greedy makes it to be. And maybe we can reduce these options here also, I guess. This much does not make sense. Yeah. So let's just say we just need to check three options. Why are we needing to check five options? The question still remains the same. Okay. So the problem is asking, so we need to proceed option by option here. We'll need to see for every option what the greedy selects and whether that is optimal or can we make it better. And for checking, can we make it better than the greedy one? We'll just need to do it manually, like checking ourselves manually. So there is no algorithm as of yet which we have discussed for this problem, like how to make this in optimal number of coins. So we just need to check it manually, like we did in the previous question this, that, whether there is a better solution than the one given by the greed. So yeah. So let's just say the coins given to us are 6, 1, 6, 5, 7. So I'll just write it in a sorted manner because that makes our life much easier. So 1, 5, 6, 7, and X is 15. So we need to make X as 15. So using the greedy algorithm, the greedy algorithm will be doing is it selects the largest denomination coin, which is 7. And since 7 is less than 15, it will select 1, 7. And then this X becomes 8. I'll just be discussing this a bit fast. So this X becomes 8. And as soon as X becomes 8, it again selects a 7. And X becomes 1. And it selects 1. The greedy algorithm selects 7, 7, 1. So greedy algorithm actually selects three coins, which are 771. And actually, what you will observe is that this is the optimal solution. So, like any algorithm will need at least three coins. And why is this the case? Because the largest denomination which we have is a seven denomination. So even if we were to use this seven as much as possible, 15 divided by seven, the thus the smallest integer greater than the value 15 by 7 is 3 only. So we'll need anyways 3 coins no matter what algorithm we choose. But since 15 by 7 is uh, this is maybe I'll just write like this. This is optimal as every algorithm requires at least 3 coins. This is because 7 is the largest denomination, but 15 by 7 is greater than 2. So what this actually means is that 50, since 15 by 7, the largest denominations, even by using the largest denomination, we won't be able to obtain something in 2 coins. So yeah, that's why this option is correct, and this is actually optimal. Option A is optimal. So option B is something like coins is, again, I just write it in a sorted manner. Coins is 1, 2, 5, and 10. And X is actually equal to 25. So note that in this problem, I think this kind of example was discussed in the lectures already that uh, we can, so if the coins is of this format that they are 1, 2, 5, 10, then actually we can always, then greedy algorithm always works. And why is this the case? Because suppose the greedy algorithm was, okay, maybe let's just look at the, maybe let's just not look at the argument, but let's just look at here only. So what the greedy algorithm selects here. So again, greedy algorithm selects a 10, 10, and a 5. So greedy algorithm, maybe these arguments will follow similarly here also. The greedy algorithm here, what it selects is a first a 10, then another 10, then it selects a 5 to make this 25. This is optimal as every algorithm requires 3 coins. And why is this the case? Because 25 divided by 10, because 10 is the largest denomination, but 25 divided by 10 is greater than 2. So I hope this argument is clear to everyone. So this is optimal. So option B was optimal. Let's just look at option C now. Option C is 1, 2, 5, 8, 9, 10. So something like this. And X is 17. So now here what greedy algorithm selects is the greedy algorithm selects. So what it selects is it first selects a 10, then only 7 remains. So it selects a 5 and then a 2. Selects 10, 5, 2. So I hope it's clear to everyone how we arrived at this. Just select the highest denomination. After selecting 10, only 7 is left, and 7 can only be collected by this 5 largest and then a 2. So this greedy algorithm here uses 3 coins. But what we claim here is actually, so this has been written by Rahul also in the chart. Okay, okay, Rahul, uh, I did not see your message earlier. Sorry for that. So yeah, so Rahul is asking in the previous question, the algorithm which Rahul suggested. So Rahul suggested an algorithm. So Rahul, you suggested a greedy algorithm for this question for finding the optimal solution. But trust me, there will be a counterexample for that also. So there will be an example in which your algorithm will not work. So I don't know the example right now, but there will exist an example. That's for sure. Okay. So now coming back to this, so Rahul has given the answer in chat earlier that option C is correct. So yeah, actually, the greedy algorithm here is not optimal. So you can see the greedy algorithm uses 3 coins, but actually this is not optimal. And why is this not optimal? This sum of 17 could have been made if we had just used these 2 coins instead, the coins 8 and 9. Okay, this is not optimal as 17 could have been made by 2 coins 7 and 8. So greedy is not optimal in this option C. It is optimal in A and B. So choose all counterexamples which prove that greedy is not optimum. So option C is the only option here. So just writing out the answer. Hence, option C is the correct answer. Okay, cool. So I guess this covers the problem for the day. I had one or two more problems, but I just removed them because, like, yeah, since we are out of time, sort of. So since we have something like 5 minutes left, so if any of you guys have any doubts or any comments or any suggestions, maybe you can ask via chat. And otherwise, if you don't have any doubts, maybe we can close the session. So, okay. So Ram Gopal is asking, in case data is not sorted, then sorting them is allowed in question. So, uh, so this is so obviously Ram Gopal, sorting an array takes some time. Like sorting an array using quicksort takes an n log n time or something, right? So you have to see the problem statement only, that whether an n log n time is allowed or not. If n log n time will exceed the time limit, then you most probably will not be sorting. But note that in this sort of problem, I'm not writing a code for it. I'm just solving this problem manually, right? So while doing manually, there is no issue. I can sort, I cannot sort. There are no constraints on me for solving the question, right? So I can do it as I want. But yeah, in problems of competitive programming, when you have to write the code, you will have to see according to the question whether n log n time is allowed or n log n time is not allowed. So yeah, so this was just these were just written questions, so I just did it myself. So Ram Gopal was asking for question 4. Okay, so in question 4 also, actually we needed to sort it using the n times first. Uh, Rahul, so but here the initially, like, we need to sort always in the increasing order of n times here. But here, like, we were lucky that the question already gave us an increasing order of n times. N times. So yeah, even if you write a code for this problem at least, you will need to sort. So yeah, no going away from sorting in this problem at least. So yeah. So in case it is not sorted, then you will have to sort it. So you will need to take n log n time for sorting it first. Because you all at all times you will need to find out the event with the smallest n time, right? And for finding it, you will need sorting. So yeah. So in case of not sorted, you will have to first sort it and then proceed. This is what I believe. Maybe I'm wrong, but I don't like I don't think I'm wrong. Like, I'm pretty sure that you will need to sort it if it is not sorted. Okay. Okay, and thanks for the compliment, Rahul. So yeah. So yeah. So I guess since no one has any other questions and it's now like close to 8 p.m. now, so I guess we can close the session. So thanks for attending this session, guys. So hopefully I'll see you guys next week also, same timing, Tuesday 6 to 8 p.m. So yeah, thanks for attending, and yeah, maybe we can close the session and you can leave the meet. Thank you, guys.